Okay, let's continue. We'll continue with chapter 3, real numbers. So, what are real numbers? So, consider the number line. Consider the number line. The points on the number line are called real numbers. So, real numbers are just points on the number line. Now, we can ask, can we add real numbers? So, here's an example. Suppose this is point x and suppose I'll take a smaller segment. So suppose this is point y, then what is x plus y? Then so on the number line, if we take the same point x and then move further, like so, add y, so to speak, then you'll get to this point. This point is x plus y, right? So you're adding y to x. So another example, suppose this point is x and this point is point y, then so x plus y can be found like this. First you take x, so take x and then add y, so to speak. So y is to the left of 0, so you move towards the left while adding y. So here this point would be x plus y. So with these two examples, it should be sort of clear how we add real numbers, how we add points on the number line. So yes, we can add real numbers. We can ask, what are the properties of addition of real numbers? So we have an observation. Addition of reals. So the observation is addition of real numbers so it agrees agrees with the addition of rational numbers. That is, for rationals m by n and r by s, their sum as reals is just equal to their sum as rationals. So for rationals, both the sums are equal. Both kinds of summations, summing them as reals and summing them as rational numbers, both give the same result. So addition agrees with the addition of rational numbers, and the addition is commutative. Addition of real numbers, addition of points on the number line is commutative. That is, order doesn't matter. A plus b is b plus a for any two real numbers a and b. Also, the addition of real numbers is associative. That is, grouping doesn't matter. So a plus b plus c grouped together is a plus b grouped together plus c. So we have associativity, and we have another property. For any real a, so 0 plus a is c, 0 plus a is a. So adding 0 to any real number doesn't change that real number. And for any real a, you have an additive inverse. There is a unique real minus a such that a plus minus a equals 0. So you have additive inverses. We call minus a the additive inverse of a as usual. So these are the main properties of addition of real numbers. So it agrees with addition of rational numbers. It is commutative, that is, order doesn't matter. It is associative, that is, grouping doesn't matter. So adding 0 to any real number doesn't change the real number. And finally, every real number has an additive inverse. So these are the basic properties of addition of reals. Now we can ask the same question about multiplication. Can we multiply reals? So this is a somewhat more difficult question. Can we multiply real numbers? Can we multiply points on the number line in a natural fashion, or any 2 points on the number line? So it turns out yes. So we will not prove it, but we will study the properties of multiplication. Okay, so any 2 points on the number line can be multiplied in a natural fashion. So here is a theorem. I'm calling this a theorem because it's somewhat non-trivial, but we will not prove it. Multiplication of reals. So how do we multiply any 2 points? So you can pause and think. You're given this number line and given any 2 points on the number line, then they may not be rational. We saw that not every point on the number line can be written as m by n, where m and n are integers. So consider any 2 points on the number line. How can you naturally multiply them to get a point, third point on the number line? So how do you do that? How do you define multiplication in a natural way? So it turns out there is a multiplication, and we'll study the properties. So for rational numbers, the multiplication was easy. You just define m by n times r by s as mr by ns, and we showed that. So we showed that that's independent of the representation of the rational numbers and so on. So we showed that. So multiplying rational numbers is easy, but can you extend the multiplication of rational numbers in a natural way to multiplying any two numbers on points on the number line? That is, any two real numbers. That is somewhat non-trivial. So multiplication of real numbers. So these are the properties. It agrees with the multiplication of rational numbers. That is, for any two rationals m by n and r by s, their product as reals is equal to their product as rationals. So multiplying two rational numbers with respect to multiplication of rationals or with respect to multiplication of reals, both of them give the same result. So it agrees with the multiplication of rational numbers. So we want this property. This is one major property which makes the multiplication of reals natural. It agrees with the multiplication of rational numbers, right? And the multiplication is commutative. That is, order doesn't matter. So AB equals BA for any two points A and B. The multiplication is associative. That is, grouping doesn't matter. So for any 3 points A, B, C, A times B times C grouped together is A times B grouped together times C. So multiplication is associative. And for any real A, so these are similar to the properties of addition. Agrees with addition, so here agrees with multiplication. Agrees, so commutativity, so here also multiplication is commutative. Associativity, so here also multiplication is associative. Order doesn't matter and grouping doesn't matter. Then for any real A, 0 plus A is A. Similarly, for any real A, so 1 times A is A. Multiplying 1 with any real number gives its A back. Adding 0 to any real number gives A back. And multiplying 1 to any real number gives A back. So similar property. And then we have multiplicative inverses. But for non-zero reals, for any real A not equal to 0. So A not equal to 0 is important. There is a unique real A inverse such that A times A inverse is 1. So we call A inverse the multiplicative inverse of A. There we had additive inverses. Here we have multiplicative inverses. Multiplicative inverse of A. Right. So, and we have one additional property. So we can ask here in this property, how does multiplication interact with or I'll just write, how does the multiplication operation interact with the addition operation? So we had distributivity, so we'll again have distributivity here. Or multiplication operation means multiplication of rationals, it's not clear, right? So I'll write multiplication of reals interact with addition of reals. So how does multiplication of reals interact with addition of reals? It turns out we have distributivity, like we had distributivity of multiplication of rationals. So distributive over plus. So we are talking about multiplication of real numbers, right? So the last property is multiplication of reals is distributive, or I'll just write in symbols. So multiplication of reals is distributive over addition of reals. So we have a times b plus c is a times b plus a times c. This is, so distributivity is one key criterion which allows us to do algebra. So distributivity, for example, a plus b whole square, because for a plus b whole square, in for where a and b are rationals, we used the fact that we used distributivity, right? A plus b whole square is a plus b times a plus b times b. So the fact that where is this? We proved that for integers, I guess, it naturally extends to rational numbers as well. But because of distributivity, we could basically do, for example, this a plus b whole square. See, we could do a plus b times we could simplify a plus b times a plus b as a plus b times a plus b times b. This is by distributivity. So by distributivity, never mind, by distributivity of multiplication over addition. So by distributivity of multiplication over addition, we could do a plus b times a plus b as a plus b times a plus a plus b times b. So same, and we could do a plus b whole cube, so on. We could do such kinds of algebra because of distributivity. So distributivity is a very key property. So how does multiplication of reals interact with the addition of reals? So multiplication is distributive over addition, that is a times b plus c is a times b plus a times c. So you have the key properties of, these are the key properties of multiplication of reals. Now we can ask, so ratio of reals, we can ask, can we define a by b for any reals a b where b is not equal to 0? So we'll define ratio of reals like we define ratio of rational numbers. Let a b be reals and b is not equal to 0. The unique real box such that b times box is a is called a by b, is denoted by the symbol a by b. Okay, this is how we define ratio of reals. And observation, this is about the ratio of reals. So we have defined ratio of reals, but its existence is not clear, right? So this observation will make it clear. Let a b be reals, b not equal to 0. Then this symbol a by b defined above, the unique point box such that b times box is a. So this point a by b exists. Further, a by b is just the multiplicative inverse of b times a. So multiplicative inverses exist by our description of the multiplicative inverses exist for any non-zero real. So b is not 0, so multiplicative inverse of b exists by the above description. So b inverse a exists. It turns out that a by b also exists, and a by b is just b inverse a. So we'll prove that b inverse a acts as, so we'll prove first the existence part. We need to show the unique real box such that b times box is a. So existence, so consider b inverse a. We have b times, we have b times b inverse a equals 1 times a equals a. Hence b times box equals a for box equals b inverse a. So we could find a point such that a point box such that b times box is a. We could find that. So existence of such a box is clear. So to show that a by b exists, we need to show that this box which we considered b inverse a, this is the unique box such that b times box is a. So we'll show uniqueness. Say b times box equals a for some real a. So for some real box, multiplying by b inverse both sides, we get box equals b inverse a. From first part we showed that b times box is equal to a for box equals b inverse a. Secondly, we showed that starting from b times box equals a, we get that box equals b inverse a. So box equals b inverse a can be the only point such that b times box is equal to a. So from 1 and 2, we see box equals b inverse a is the unique real. Unique real is the real. So the is part is from 1 and the unique part, this is from 2. Or I'll just write one bracket. So this is the unique real. The is part is from 1. Existence is from 1. Box equals b inverse a is the unique real box such that b times box equals a. So by the definition of a by b, hence a by b exists and is a by b equals b inverse a. So we showed that the ratio of any two real numbers defined as above. So ratio of any two real numbers a and b where b is not equal to 0. This is the definition. The unique point such that b times that point is a. That point is called a by b. So we showed that a by b exists and a by b is just the multiplicative inverse of b times a. So we showed this like we did for rationals. So for rational m by n, the multiplicative inverse was n by m, and for a rational m by n, we defined a by b is the unique rational So let a, b be rationals, b not equal to 0. The unique rational box such that b times box is a, we call that a by b. So we have defined ratio of rationals, and does a by b exist? So we have this similar observation. Let a, b be rationals, b not equal to 0. Then a by b, the ratio of two rationals as defined above exists, and a by b is just b inverse a. So we see here also we can write is, the is part is from 1, that b inverse a is a rational box such that b times box is a, that is from 1, is the unique rational, this is from 2. If at all a box satisfies b times box is equal to a, that box should be b inverse a, we got it from 2. So b inverse a is the unique rational box such that b times box is equal to a. So this is about ratio of rational numbers as defined above, and we have extended the definition to ratio of any two real numbers where a and b, where b is not equal to 0. So here also we can ask, after defining we should always ask the question, does that defined quantity exist? Does a by b exist for any reals a, b, where b is not equal to 0? So this is what we showed, like with rationals, ratio of rationals. So okay, so these are the basic properties of addition and multiplication. We looked at basic properties of addition and multiplication of real numbers. Real numbers are just points on the number line. We looked at the properties of addition of points on the number line and multiplication of points on the number line, and taking ratios of points on the number line. Okay, so that's all for this part. See you in the next part.